Hi everyone, welcome back to our second lesson in our unit on astronomy. So last time we kicked off the unit by just talking a little bit about some of the basics of stars, what they are, their temperature, how we're able to figure that out, as well as how stars change over the course of their lifetime. We're going to dig in a little bit more today by looking at what stars are made of and how those stars are able to produce the light that we are able to see and enjoy here on Earth. So let's go ahead and dive on in. Okay, so as we've seen, there are lots of stars, lots and lots of stars, and they vary along a variety of different dimensions. We already talked about a number of those differences in our last lesson, talking about color, temperature, changes in size over the course of their lifetime, differences in brightness along that HR diagram, and then how the stars change as they age. Today, again, we're going to be focusing in on composition. And by composition, I just mean what is it made of? What is a star? What is in a star? So how can we tell what is in a star? Well, we really only have one thing to go off of when we study any star, and that's the light that it gives us. We can't really go to the star and collect up a sample and analyze it. Like we just have the light to go off of. Now, in our previous lesson last time, we looked at these blackbody radiation curves, which show us the different wavelengths of light that are being emitted from a particular star. And we talked about how, last time, we talked about how the peak of this radiation curve is determined by the star's temperature. All right, so cooler stars appear more red, hotter stars appear more blue, and then there's yellow and white in between the two of them. So we already know that we can use light to determine the temperature of a star, but we can also use that light to determine what's in the star. Okay, so we've already looked at this radiation curve and we said, oh, we've got this nice little peak here and then it kind of dips off and everything. But that's not the whole story. Okay, so when we're really zoomed out of the emission curve, that's what it looks like. But if we zoom in on that curve that you see here of the amount of different wavelengths that are being radiated by a star, we see something interesting. There are these little gaps in that curve. And so you can see that right here. So again, this is just zoomed in on that same radiation curve that we were looking at last time. So wavelength on the x-axis and like the intensity of the light at that wavelength along the y-axis here. All right. Now, before we just sort of simplified and created something kind of similar to the blue line here, where it's just this nice continuous, like gradual curve here. But if we look at the actual amount of light being emitted by a star at different wavelengths, it actually looks more like the red curve that you see here, okay? And so that red curve is what we would call an emission spectrum, where we're really seeing like, okay, what are the different wavelengths that are being produced by this star, being emitted by this star. And what I hope you'll notice looking at this red curve here is, yeah, it's a little bit jagged, but in particular, there are a few places where we see these really dramatic dips, all right? So we're kind of like hanging out, and then whoom, suddenly there's like a significant lack of this one particular wavelength. And then we go back and it's like, kind of noise, and then whoom, there's another dramatic dip there. And so we see there are a few specific wavelengths that aren't really being emitted by the star as much as we would expect. There's this noticeable absence of a particular wavelength. And so then the question becomes, why not those wavelengths? Where did those wavelengths of light go? Why aren't they being emitted and sent to us like the wavelengths immediately on either side of them? What's special about those wavelengths of light? All right. Now, to understand that, we got to go back to a little bit of basics of atomic theory, which seems weird. I know we're talking about like big stars, and now I'm like, let's pull it back in to teeny atoms. Okay, but let's do that. It's all going to come together, I promise. Okay, so the Bohr model of the atom has the basic idea that an atom consists of a little positively charged nucleus at the center, and then there are a bunch of electrons around the outside. You already know this. Yes? Yes. Good. All right, wonderful. So, so we've got these electrons orbiting around the outside, and there are these different energy shells, basically. Those electrons can have different amounts of energy. And so if we shoot some energy at our atom at a particular amount, the electron is able to jump up to a higher energy level. And so we see that here. We've got an electron represented in green right here. It starts off at the second energy level, but if we shoot some energy, in this case in the form of light, at it, it's able to jump up to the next energy level right there, okay? But the thing is, each atom has very specific energy gaps between its different energy levels. It can't just accept any amount of energy and use that to jump up, use that to get its electron to move up to a higher energy level. It has to be the exact right amount, the exact difference in energy for it to make that leap, okay? So, so the energy gap between these different levels is really, really important, okay? So we can study that a little bit further by looking at atomic spectra, okay? So let's start off with this first one here that says hydrogen, okay? And so what you're seeing right now is this big black rectangle with a few specific lines of different colors, okay? Now this represents the spectrum of hydrogen, which basically means that if you were to shoot a bunch of white light of a bunch of different wavelengths, all these different wavelengths, at hydrogen, these specific wavelengths, 410.1 nanometers, 433.9 nanometers, and so on and so forth, wouldn't make it out the other side, because those are the amounts of energy that hydrogen can use to bump its electrons up to the next energy level. Okay, and similarly, if you were to heat up the hydrogen really, really, really hot, those are the amounts of energy that would be emitted from it as well. Okay, so these are sort of the special wavelengths associated with hydrogen. Those are the amounts of energy that hydrogen can use to have its electrons jump back and forth between energy levels. Okay, and then down beneath the hydrogen one, we see the spectrum for helium. So we see that's different. All right, so these two atoms have different energy gaps between their different energy levels, and so they use different wavelengths of light in order to move their electrons around from one energy level to the next. Now, if this is very exciting for you, I've gone ahead and linked for you a simulation that allows you to see more of these spectra for any element that you would like. So all you got to do is just click on an element. Let's try carbon. Everyone loves carbon. We'll increase the line intensity, and you can see the exact wavelengths then that carbon uses to move its electrons around from one energy level to the next. So if you want to geek out, go for it. It's great, okay? So we have then, for each of these different elements, specific wavelengths that are usable for the elements, and the other wavelengths they don't really care about because those aren't the right amount of energy to get their electrons to jump from one energy level to the next, all right? So if then we go back to the emission spectrum from a star, and we see where those little dips are, there's something kind of special about them. So this particular spectrum comes from a sun-like star, and if we go through and compare where the dips are, which wavelengths are absent from the emissions from the light being produced by this star, we see that they line up with a lot of the same wavelengths that hydrogen is able to use, okay? Which is like, whoosh, okay, so it seems like just random dips, but they're not random. Those happen to be the exact same wavelengths that hydrogen is able to use to get its electrons to jump from one energy level to the next. So what that tells us then is that this star must contain hydrogen. That probably the star is actually producing all of those wavelengths. But what happens is when it's producing that light, the hydrogen atoms in sort of the outer layers of this star use up that energy to move their electrons before that light is able to reach us here on Earth. Okay, so then this is how we're able to figure out what is in stars. is by looking at which wavelengths are missing and what elements might have been responsible then for stealing those wavelengths before we were able to see them here on Earth. Is this not wild? This is wild. Okay, so that's how we're able to figure out what a star is made of, is just by looking at what light is absent and who are the culprits, what are the elements that are going to steal that light before we're able to see it here on Earth. Okay, so that's how we figure out the composition. So to go back then to the whole process of stellar evolution and the different types of stars, let's go ahead and fill in what are the different elements that we see present in some of these different stars. Okay, so in a main sequence star, where the star is for most of its life, we see that there's a lot of hydrogen in those stars. There's some helium as well, and maybe a little bit of some other things too. So like Sirius is a high mass star, and pretty much its spectrum really nicely lines up with just hydrogen and helium. That's pretty much all we're seeing in Sirius. The sun also is mostly hydrogen and helium, but we've got a few other elements in there as well: lithium, sodium, magnesium, a couple other things. Okay, but mainly hydrogen and a good amount of helium, and those are the main players in a main sequence star. Okay, as we move on to a red giant or a red supergiant, we'll still see good amounts of hydrogen for sure, but a little bit less than we saw in the main sequence stars, and we see more helium and a greater variety of other elements as well. And we'll see a bunch of different elements all the way up to iron, which is atomic number 26, meaning that it has 26 protons in it. Okay, so that's what's going on right there. Whoops, sorry. Now, for an average star, if it goes over and becomes a planetary nebula and becomes a white dwarf, from white dwarfs, we just see carbon and oxygen, and that's pretty much it. We do not see hydrogen, unlike in our other stars. And then supernova, supernova are fun, okay? So I said that in red giants and red supergiants, we see elements all the way up to iron. That's not really where the periodic table ends. All the heavier elements that are naturally existing are coming from the supernovas. So cool, look at that. All right, and then lastly, neutron stars are called neutron stars because they're made of neutrons. Okay, so that's what's happening there. You get a bunch of protons and electrons that all smash into each other to form neutrons. That's sort of the Cliff's Notes version of what's going on in there. So so that's what's happening in all of these different stars. Now let's take a moment then to just try to identify, okay, what does this all mean? What is the bigger pattern that this is pointing to? So I've got a table here on the right that just sort of summarizes, okay, the type of star, and then what elements we tend to see in those stars. And then over on the left, I've got a periodic table for you, and I've tried to kind of color code things so that you can kind of see where each of the relevant elements for each of our stars is located on that periodic table. So take a moment and just consider, what's the big pattern? What do you notice changing about the composition of the star throughout the course of its lifetime? So what I hope you're seeing is that in general, stars start off with lighter elements, and then over the course of their lifetime, they're made up of more and more heavier elements, all right? With the exception of white dwarfs, because they kind of are losing a bunch of their outer layers because of the planetary nebula, so, you know. But in general, we're moving from lighter to heavier on the periodic table here. And so the reason for that really gets at the heart of what actually is powering these stars and what they're doing and how they're able to produce light. Okay, so let's throw it way back, all the way back to the Big Bang, which we're going to be getting into next time. It's going to be great. Okay, and if we think about, you know, the very origins of the universe and the first elements that were being produced, what element do you think would be the simplest, the first one that was produced at the start of the universe? Well, you can't get a lot simpler than just one proton, which means that hydrogen was the first element to form at the beginning of the universe and is still the most prevalent element throughout the universe today. Okay, so we got lots and lots of hydrogen, atomic number 1. But it doesn't stay that way, because as we form our stars from those stellar nebula, right, and you get all of these atoms and little bits of stardust coming together, being pulled together by gravity, the temperature goes up, the pressure goes up, and those are the right conditions for nuclear fusion to occur. All right, so what's actually happening then in these stars is that lighter elements are getting smashed into each other and combining together to make heavier elements. All right, so we see an example of this in the diagram here, where we've got a hydrogen atom and another hydrogen atom, and they're running around in the core of this main sequence star, and things are going, and then boom, they smash into each other and they combine together to form a helium atom. So we go from atomic number 1 to atomic number 2. We're getting heavier over time. And a byproduct of this nuclear fusion reaction is light. And so that's why then these stars are producing light, is because they have billions upon billions of these nuclear fusion reactions happening constantly. And each of those reactions is producing a little bit of light for us. So that's what's happening with the sun. The light that we are seeing is just a fortunate byproduct of the sun working hard to fuse hydrogen together into helium and so on and so forth into heavier elements as well. And just so you know, this is really actually how we were able to determine the how stars change over the course of their lifetime, because obviously we weren't able to just sit there and watch stars change from main sequence into red giants into white dwarfs. Like that is way in a time scale way beyond what we are able to do. But what we've been able to do is kind of reason through, once we see what each of these stars is made of, we're like, well, hydrogen's simpler than carbon, for example, and so if a star has a lot of hydrogen, it's probably younger than a star that has a lot of carbon. And so that's actually how we've been able to figure out how stars change over the course of their lifetime. All right, so then just to kind of revisit our narrative for how stars evolve over time with this new information about the nuclear fusion that is powering all of this progress. All right, so we start off with our stellar nebula, okay? And basically we've got all this stardust, all these little elements just kind of floating around out there in the universe, and most of them are hydrogen because the universe is mostly hydrogen, because it's the simplest, it's the easiest to make, so that's where we have it. Okay, so so that's what's going on in our stellar nebula, right? And so then that stardust kind of condenses together to form our protostars and then our main sequence stars. Now again, all that stardust is mostly hydrogen still. Okay, so our main sequence stars then, as they come together, are primarily focused on fusing that hydrogen together into helium. And then as they continue to get hotter and do all these other things, and they're able to kind of build heavier elements as well. But in the beginning, it's just hydrogen to helium for the most part. Okay. And then as our main sequence stars run out of hydrogen in their core, so the core is the hottest part, that's where we're seeing most of the nuclear reactions. As we start using up all of that hydrogen that's there in the core, because that's the hottest part and where we get the most reactions, we start moving those reactions out into the outer layers of the star. And so that is what causes our main sequence stars to expand out into red giants and red supergiants as we're moving from the inner layers to the outer layers, those hydrogen fusion reactions, right? Now for average mass stars, eventually what happens is that outward radiative pressure is too great for gravity to kind of hold it all in. We lose those outer layers. All that is left is this carbon and oxygen core that's hanging out. There is no longer hydrogen getting fused. And at this point, we say that the star has essentially died. It's sort of at the end of its life at this point, because it no longer has nuclear fusion reactions powering it. We're just sort of seeing residual light that's still bouncing around there. That's being emitted from the star, but it's not continuing to fuse different nuclei and produce more light at that point. Okay. So that's the fate of average mass stars, but we know that high mass stars, they explode in this very dramatic supernova. And supernova are the one thing in the universe that have enough energy to create those heavier elements beyond iron. Okay, so anything heavier than iron came from a supernova. And that's true everywhere in the universe. And so what I want you to take a moment then as we wrap this up to just kind of ponder and think about is that everything around you, everything you see here on Earth, all these different elements, for the most part, were made by stars. All right, so all this stuff, all these raw materials, these elements that we have, those are the products, the outcome of stars before us working hard to fuse hydrogen into heavier elements. And that includes then the elements that make up you and me. Because we're not just made of hydrogen, we're made of a lot of other elements that are much heavier than hydrogen. And what that means is you are the child of a star. The elements that make up you came into existence inside a star. So you are made of stardust, and old stars, former stars, live on in you and all the other people around you. And so if you don't remember anything else from today, I hope you'll at least take away that one little nugget, that everyone and everything around you is just made up of stardust and deserves to be treated with love and respect accordingly. All right. That is all I have for you today. Please, please, please ask me your questions. I will do my best to answer them. And have a wonderful, wonderful day. Love you lots. Miss you. Bye.